Welcome back to the Midnight Vessel. The rock beneath your feet is moving. Not fast, you will never feel it, never notice it in a lifetime of standing on it, but it is moving, has always been moving, carrying everything built on top of it across the face of the planet at the speed a fingernail grows. The cabin is warm tonight, the round window looking out onto dark water and the faint outline of coastal cliffs in the distance, their layered faces just visible in the moonlight, each stripe a different era, stacked one on top of the other, like the pages of a book no one has ever read in full. The geological maps are spread open on the desk, and the rock samples sit patient and dense and indifferent to the hour. The fire is low, the ship is still, and the earth beneath all of it is doing what it has always done, moving slowly, without stopping, without ever needing anyone to notice. The earth is not a solid ball. From the outside, it appears that way, a smooth blue sphere, hard-edged and permanent. But the interior is a layered structure of radically different materials, each behaving differently under the pressure and temperature of its depth. The outermost layer, the crust, is the thin shell we live on, ranging from about 5 kilometers thick beneath the ocean floors to up to 70 kilometers thick beneath the continents. Relative to the planet as a whole, it is thinner than the skin of an apple. Below it lies the mantle, nearly 3,000 kilometers of hot, dense rock that behaves as a solid on short timescales, but flows like an extraordinarily thick liquid over millions of years, driven by heat rising from deep below. Below the mantle lies the core, divided into two distinct regions. The outer core is liquid iron and nickel, circulating in slow convective currents that generate the Earth's magnetic field, the invisible shield that deflects the solar wind and protects the atmosphere from the stream of charged particles the sun constantly emits. Without it, the planet would slowly lose its atmosphere, the way Mars did billions of years ago. At the very center is the inner core, a solid sphere of iron and nickel, roughly the size of the moon, under pressure so extreme that despite temperatures exceeding 5,000 degrees Celsius, the metal cannot melt. It is the hottest place on Earth and one of the least understood. Everything we know about it was inferred from the way earthquake waves move through it. The way we know what lies inside the Earth at all is through seismology, the study of how seismic waves travel through the planet's interior. When an earthquake occurs, it sends two types of waves radiating outward: P waves, which can travel through both solid and liquid, and S waves, which can only travel through solid material. By recording how these waves arrive at seismometers around the world, how fast they travel, where they bend, where they stop, geologists can map the Earth's interior without ever drilling into it. The liquid outer core was discovered in 1914 by seismologist Benno Gutenberg, who noticed a shadow zone on the far side of large earthquakes where S waves failed to arrive. The waves had hit something liquid and stopped. The planet's interior was revealed not by digging but by listening. The heat driving all of this comes from two sources. Some is primordial residual heat from the planet's violent formation 4.5 billion years ago, energy that the Earth has been slowly radiating ever since. The rest comes from radioactive decay, the slow breakdown of uranium, thorium, and potassium in the mantle and crust, each event releasing a small amount of heat that, accumulated across the entire planet over billions of years, amounts to an enormous continuous energy source. The Earth is, in a sense, a nuclear reactor, not designed, not controlled, but a planet-sized accumulation of radioactive material, slowly releasing energy locked inside it since the solar system formed. That energy moves the plates. That energy is what the stone remembers. The mantle convex hot material rises, spreads, cools, and sinks again in slow cycles that drag the crustal plates along on their surface like objects floating on a very slowly boiling liquid. This is the engine beneath plate tectonics, beneath the earthquakes and volcanoes and the slow drift of the continents, a heat engine 4.5 billion years old, gradually winding down but still far from finished. The cliffs visible through the cabin window tonight were not always where they are. The ocean they face was not always an ocean. In the next passage, we follow what happens when that engine drives the plates into motion and into each other. 250 million years ago, there was no Atlantic Ocean, no Indian Ocean, no Mediterranean Sea. The continents we know, the shapes we learnt in childhood, the outlines that feel as permanent as anything on Earth did not exist in their current form. In their place was a single, enormous landmass called Pangaea, surrounded by a single global ocean, its interior so vast and so far from any coast that the center of it received almost no rain, a continental desert larger than anything on Earth today. Pangaea was not the first supercontinent. It was merely the most recent, the last in a series of assemblings and breakings, cycling for at least 3 billion years. The continents have been moving for as long as there have been continents. They are moving now. The theory of plate tectonics was not accepted by mainstream geology until the 1960s. The basic idea had been proposed decades earlier by the German meteorologist Alfred Wegener in 1912, who noticed that the coastlines of South America and Africa fit together like puzzle pieces, that the same fossil species appeared on continents now separated by thousands of kilometers of ocean, and that matching geological formations appeared on opposite sides of the Atlantic. His explanation that the continents had once been joined and had drifted apart was rejected by most geologists of his time, who could not conceive of a mechanism powerful enough to move entire continents. He died in 1930 on the Greenland ice sheet, his theory still widely dismissed. Within 30 years of his death, ocean floor surveys had provided exactly the mechanism he lacked, and plate tectonics became the foundation of modern geology. The ocean floor is not ancient. This was one of the most surprising findings of 20th century geology, that the sea floor is constantly being created at mid-ocean ridges, where tectonic plates pull apart and molten rock wells up to fill the gap, solidifying into new oceanic crust and spreading outward in both directions. The oldest oceanic crust anywhere on Earth is only about 200 million years old, a fraction of the planet's age, because oceanic crust is continuously recycled, created at ridges and destroyed at subduction zones, where it dives back into the mantle. The Atlantic Ocean is currently widening at about 2.5 centimeters per year, roughly the rate your fingernails grow. In 100 million years, it will be significantly wider than it is tonight. There are 3 types of plate boundaries, and each produces a different kind of geology. At divergent boundaries, plates move apart and new crust is created. At convergent boundaries, plates collide when an oceanic plate meets a continental one. The denser oceanic plate dives beneath the lighter continental crust in subduction, generating deep ocean trenches, volcanic arcs, and the earthquakes of the Pacific Ring of Fire. When 2 continental plates collide, neither can subduct, both are too buoyant, so the crust crumples and thickens, pushing upward into mountain ranges. The Himalayas are the ongoing result of India colliding with Asia, a collision that began 50 million years ago and has not yet finished. At transform boundaries, plates slide horizontally past each other, generating earthquakes without creating or destroying crust. The San Andreas Fault is one of the most studied of these on Earth. Pangaea began breaking apart about 200 million years ago, driven by the same mantle convection that had assembled it. The North Atlantic opened first, then the South Atlantic, then the Indian Ocean, each rift beginning as a zone of crustal stretching and volcanism that gradually widened into a new sea. The process has not stopped. East Africa is currently being pulled apart along the East African Rift, a zone of volcanism and thinning that, in tens of millions of years, may open a new ocean and separate the eastern horn of Africa from the rest of the continent. The map of the world is not finished. It has never been finished. Every map ever drawn has been a snapshot of a process already well underway before the first human looked at the ground and wondered what lay beneath. The ammonite fossil on the desk was once a living creature in a sea that no longer exists, above a seafloor long since subducted back into the mantle, on a piece of crust that has travelled thousands of kilometres from where it formed. The rock it is preserved in remembers all of this in the only language rock knows, the language of pressure and chemistry and the slow accumulation of time. In the next passage, we look more closely at that language, at the 3 kinds of rock, how they form, and what each one preserves of the world that made it. Pick up any rock and you are holding a record. Not a written one. Rock has no language, no intention, no awareness of what it preserves. But in its mineral composition, its texture, its layering, its chemistry, it contains a precise and readable account of the conditions under which it formed, the temperature, the pressure, the presence or absence of water, the depth below the surface. Every rock is an autobiography of the circumstances that made it. and because rocks can be dated, their ages measured with precision using the decay of radioactive isotopes, every rock is also a timestamp, a fixed point in the 4 billion year story of the Earth's surface. The 3 rocks sitting on the desk tonight each tell a different kind of story in a different kind of language. Igneous rocks are born from fire. They form when magma cools and solidifies, either underground or at the surface, and the difference between the two produces dramatically different textures. Magma that cools slowly deep underground crystallizes gradually, allowing large mineral grains to grow, producing coarse-grained rocks like granite, whose individual crystals are visible to the naked eye. Magma that erupts at the surface cools quickly, giving crystals little time to form, producing fine-grained rocks like basalt, the dark dense rock that makes up most of the ocean floor, and the volcanic islands of Hawaii. Some lava cools so fast it solidifies before any crystals form at all, producing obsidian volcanic glass, smooth and sharp-edged, used by prehistoric humans to make some of the finest cutting tools ever made. Sedimentary rocks are the archives. They form at the surface from the accumulation of particles eroded from older rocks, carried by water or wind, and deposited in layers that gradually compact and cement into stone. Sandstone preserves ancient deserts and riverbeds. Limestone preserves shallow tropical seas, composed almost entirely of compressed shells and skeletons of marine organisms. Shale preserves ancient lake and ocean floors, its thin layers recording seasonal and climatic variations with extraordinary sensitivity. Sedimentary rocks cover about 75% of the Earth's land surface, and they are where almost all fossils are found, organisms buried in sediment before they could decay, their hard parts slowly replaced by minerals over millions of years. To read a sedimentary sequence is to read time directly, each layer younger than the one below it, each one a chapter in a story spanning hundreds of millions of years. Metamorphic rocks are what happens when existing rocks are subjected to extreme heat and pressure without melting the minerals, recrystallizing into new forms, the original rock transformed but not destroyed. Limestone becomes marble, shale becomes slate, then phyllite, then schist, then gneiss, each transformation recording a step deeper into the Earth's crust. The metamorphic rocks exposed at the surface today were once buried kilometers deep, brought back up by the slow uplift of mountain ranges and the patient work of erosion. They are the deepest rocks we can touch, the ones that have been closest to the conditions of the mantle without quite entering it, and their textures record the pressures and temperatures they survived on the way back up. The 3 rock types are connected in a cycle that has been running without interruption since the Earth had a solid crust. Igneous rocks weather and erode into sediment that becomes sedimentary rock. Sedimentary and igneous rocks, buried deep or subducted, are metamorphosed by heat and pressure. Metamorphic rocks melt back into magma that cools into new igneous rock. The cycle has no beginning and no end, only transformation. The minerals in the rock samples on the desk tonight have been through this cycle multiple times, in forms unrecognizable from their current ones, across timescales that dwarf the entire history of complex life on Earth. The rock does not remember these transformations the way a mind remembers. It carries them the way a body carries its history, written in structure, not in story. Radiometric dating allows geologists to assign precise ages to rocks by measuring how much of a radioactive isotope has decayed in a sample. The technique works because radioactive decay happens at a fixed, known rate, regardless of temperature, pressure, or chemical environment, an atomic clock that cannot be reset by any geological process. Using different isotopic systems, uranium lead for the oldest rocks, potassium argon for volcanic deposits, carbon 1,4 for organic material up to about 50,000 years old. Geologists have constructed a timescale for Earth history with a precision unimaginable to the scientists of the 19th century who first recognized that deep time existed. In the next passage, we look at what happens when the Earth releases its stored energy suddenly at the earthquakes that move in seconds what the plates take millions of years to build. On the 22nd of May, 1960, the ground in southern Chile began to move. It kept moving for approximately 10 minutes, an eternity in seismic terms, most earthquakes lasting only seconds. When it stopped, the Valdivia earthquake had released more energy than any other earthquake in recorded history, a magnitude of 9.5, so powerful that it set the entire planet ringing like a bell, detectable on seismometers everywhere on Earth for days afterward. The tsunamis it generated crossed the Pacific, killing people in Hawaii, Japan, and the Philippines. The coastline dropped by as much as 2 meters in some places and rose by several in others. The landscape was permanently altered in minutes by processes the plates had been building toward for centuries. The spring, wound for a very long time, had finally let go. An earthquake is the sudden release of energy stored in the Earth's crust as elastic strain. As tectonic plates move, the rock at their boundaries does not slide smoothly. It is locked by friction, bending and accumulating stress as the plates continue their slow motion. The rock deforms elastically, like a spring being wound tighter, storing the energy of plate motion as potential energy in strained rock. When the stress finally exceeds the frictional resistance holding the fault in place, the locked section ruptures, the two sides snap into new positions, and the stored energy is released as seismic waves radiating outward in all directions. The rupture can propagate along the fault at several kilometers per second, the ground on either side lurching meters in seconds after being locked in place for decades or centuries. Seismic waves come in several types and do different things to the ground as they pass. P waves are compressional, pushing and pulling the rock in the direction the wave travels. They move fastest and arrive first. S waves are shear waves, moving rock perpendicular to the direction of travel. They arrive second. Surface waves travel along the Earth's surface rather than through its interior and are generally the most destructive, the rolling, undulating motion that causes buildings to sway and ground to crack. The interval between the arrival of P waves and S waves at a seismometer tells you how far away the earthquake occurred. With readings from 3 or more stations, the location of any earthquake can be pinpointed precisely anywhere on Earth. The planet is instrumented now. We are always listening. The moment magnitude scale is logarithmic. Each whole number step represents a 10-fold increase in ground motion and roughly a 32-fold increase in energy released. A magnitude 7 releases roughly 1,000 times more energy than a magnitude 5. The 2004 Indian Ocean earthquake magnitude 9.1 released more energy than all the world's earthquakes in the preceding decade combined, triggering a tsunami that killed over 200,000 people across 14 countries. The energy came not from any external source, but from centuries of tectonic stress accumulating at a subduction zone, centuries of plates grinding against each other, winding the spring released in approximately 8 minutes. 8 minutes to undo what centuries had built. The places where earthquakes cluster are not random. They trace the boundaries of tectonic plates with extraordinary precision: the Pacific Ring of Fire, the collision zones of the Himalayas and the Mediterranean, the mid-ocean ridges spreading beneath every ocean. Japan, located at the convergence of 4 tectonic plates, experiences more earthquakes than almost anywhere else on Earth, a geological fact that has shaped its architecture, city planning, and the ancient cultural concept of mono-no-aware, the bittersweet awareness of how quickly things pass. The Earth teaches patience differently in different places. In some places, it teaches it suddenly. Early warning systems now exist in Japan, Mexico, and several other seismically active regions, networks of sensors that detect the fast-moving P waves and transmit alerts before the more damaging waves arrive. The warning time is short, seconds to tens of seconds, but enough to stop trains, open fire, station doors, pause surgeries, alert people to take cover. It is not prevention. The earthquake will happen regardless. It is instead a small negotiation with deep time, a few seconds carved from the gap between the moment the rock breaks and the moment the shaking arrives, borrowed from the speed difference between 2 types of waves to do what can still be done. In the next passage, we look at what happens over much longer timescales, at how mountains form, and how, grain by grain and drop by drop, they are slowly taken apart again. The Himalayas are still rising. Not fast, about 5 millimeters per year at the peaks, roughly the thickness of a coin, but rising nonetheless, pushed upward by the continued collision of the Indian subcontinent into the Eurasian plate that began 50 million years ago and has not yet finished. At the same time, erosion is eating them away: rain, ice, wind, and rivers carrying the mountain grain by grain toward the sea, depositing the dissolved remnants of the highest peaks on Earth in the deltas of the Ganges and the Brahmaputra. The mountain is simultaneously being built and dismantled, the tectonic uplift and the erosional destruction in a slow equilibrium, that determines the height at which the peaks stabilize. Every mountain range on Earth is a temporary feature, a current balance point between the forces building it and the forces wearing it down. There is no such thing in geological time as a permanent mountain. Mountains form in several ways, each leaving a different signature in the rock. Fold mountains like the Himalayas, the Alps, and the Appalachians form at convergent plate boundaries where colliding continents crumple the crust into enormous waves of rock, the layers folding and faulting and thickening as the collision continues. Fault block mountains form where the crust is being pulled apart along rift zones where large blocks of crust drop along normal faults, leaving adjacent blocks standing higher as ranges. Volcanic mountains form where magma reaches the surface either at subduction zones, feeding explosive stratovolcanoes, or at hotspots where plumes of unusually hot mantle material punch through the crust to build the broad shield volcanoes of Hawaii. Each type records a different chapter of the plate tectonic story. Each one is temporary in ways only deep time can reveal. The Grand Canyon is the most legible geological record on the surface of the Earth. Cut by the Colorado River over the past 5 to 6 million years, its walls expose nearly 2 billion years of rock layers, each one representing a different era, a different environment, a different world. The oldest rocks at the canyon's bottom, the Vishnu basement rocks, are approximately 1.8 billion years old, formed deep in the roots of an ancient mountain range that has since been completely eroded away. Above them, in sharp unconformity, sit younger sedimentary layers representing shallow seas, coastal deserts, river deltas environments that succeeded each other across hundreds of millions of years before the river arrived and began cutting downward through all of them. To stand at the rim and look down is to look at time made visible, each colored band a chapter, the river still writing the final lines. The book is open. It has always been open. Erosion is the great leveler. Given enough time, it will reduce any mountain range to a flat plain, with only the most resistant rock remaining as isolated hills above the surrounding lowland. The Appalachians, once as high as the Himalayas, have been eroding for hundreds of millions of years and now stand as gentle ridges, their original peaks long since carried to the sea. The processes doing this work are patient and various. Mechanical weathering, the physical breaking of rock by freeze-thaw cycles, thermal expansion, the growing roots of plants opens cracks and fragment surfaces, chemical weathering, the dissolving of minerals by slightly acidic rainwater, the oxidation of iron-bearing minerals weakens the rock from within. Water carries the products downhill into streams, into rivers, toward the sea. Wind lifts the finest particles and carries them continents away. The sediment carried by rivers does not disappear. It is deposited in river deltas, in lake beds, on the continental shelves, on the deep ocean floor, and begins, under the weight of subsequent deposits, the slow process of compaction and cementation that will eventually turn it back into sedimentary rock. If that rock is later buried deeply enough, it will be metamorphosed. If it reaches a subduction zone, it will melt back into magma. The mountain that erosion takes apart does not disappear. It is redistributed, spread thinly across a basin, buried, transformed, and in time incorporated into the next mountain range that forms above it. Nothing is lost. Everything is recycled. The cliffs in the round window tonight have been here for millions of years and will be here for millions more, but not always like this. In the next passage, we look at the most intimate record of all this change, the fossils preserved in the sedimentary layers, the remains of the organisms that lived in the worlds, the rocks remember. The ammonite on the desk was once alive. Not the stone object sitting there now, the creature inside the shell that the stone has replaced, mineral by mineral, over tens of millions of years. It lived in a warm, shallow sea, propelling itself through the water by jet propulsion, hunting small prey with tentacles, sensing its environment through receptors we do not fully understand. It died, sank, was buried in sediment before it could be scattered or consumed, and over the following millions of years, its shell material was dissolved and replaced by minerals precipitating from the groundwater, moving slowly through the enclosing rock. The shape survived. The organism did not. What sits on the desk is a mineral cast of a life, the most precise record the earth knows how to keep. Every fossil is a miracle of improbable survival across an almost incomprehensible span of time. Fossilization is the exception, not the rule. The vast majority of organisms that have ever lived left no fossil record, their soft tissues decomposed, their hard parts dissolved or scattered, their existence erased without trace. Fossilization requires an unlikely combination: rapid burial in fine-grained sediment before decomposition proceeds, the right chemical conditions in the surrounding rock, and the survival of that rock through hundreds of millions of years without being subducted, metamorphosed, or eroded away. The fossil record is not a complete inventory of past life. It is a highly incomplete, heavily biased sample skewed toward organisms with hard parts, toward marine environments, toward geological settings that happened to survive to the present. What we know of the history of life is a small fraction of what existed. The rest is silence, preserved in no rock, read by no one. The Burgess Shale, discovered in the Canadian Rockies in 1909, preserves in extraordinary detail the soft-bodied organisms of the Cambrian period, approximately 508 million years ago. At a time when most fossils preserve only shells and bones, the Burgess Shale preserves eyes, guts, legs, gill structures, and the fine details of animals so strange that decades of study were required to understand their basic anatomy. Hallucigenia, a creature with spines on its back and legs below, originally reconstructed upside down because no living animal provided a reference, turned out to be an early relative of modern velvet worms. Anomalocaris, once thought to be three separate animals, was eventually reconstructed as a predator up to a meter long, the largest animal of its time. The Burgess Shale showed that complex animal life had already diversified into an extraordinary variety of body plans 500 million years ago, long before anything had set foot on land, long before the ammonite existed, long before any eye had looked up at a night sky. The fossil record also preserves the endings. 5 times in the history of complex life, more than 75% of species on Earth have gone extinct in geologically brief intervals. The most severe, at the end of the Permian period 252 million years ago, eliminated approximately 96% of all marine species, an event so catastrophic that it took 10 million years for biodiversity to recover. The cause was massive volcanic eruptions in what is now Siberia, the Siberian traps that released enough carbon dioxide and sulfur dioxide to dramatically alter the atmosphere and ocean chemistry. The most recent mass extinction, 66 million years ago, ended the non-avian dinosaurs and was caused by the impact of an asteroid roughly 10 kilometers across, triggering fires, tsunamis, and a years-long impact winter that darkened the sky and collapsed the food chains built on sunlight. In the rock, both events appear as thin, dark lines, boundaries between what was and what came after. But the fossil record is not only a record of loss, it is also a record of recovery, innovation, and the relentless tendency of life to fill whatever space is made available to it. After each mass extinction, surviving lineages diversified rapidly into the ecological roles vacated by the dead, the sudden availability of empty niches, accelerating evolutionary change in ways that would not have been possible in a full world. The extinction of the non-avian dinosaurs opened the space that allowed the small nocturnal mammals of the Cretaceous to diversify into the whales and bats and primates and horses of the Cenozoic. Every extinction is also a beginning. The fossil record teaches this repeatedly, across 5 extinctions, across 500 million years of complex life, with the patience of stone. In the final passage, we step back from the detail and ask what it means to live on a planet this old, this restless, and this quietly patient. The fire has burned low. The candles on the shelves are down to their last inch, their light softer now, the shadows in the corners of the cabin deeper and warmer than they were at the beginning of the night. Through the round window, the coastal cliffs are still there in the dark, their layered faces invisible now. The strata hidden until morning brings the light back to read them by. The rock samples on the desk have not moved. The ammonite has not moved. They have been patient for tens of millions of years. Another night is nothing to them. Some forms of patience make every human concern feel very, very small. The Earth is 4.5 billion years old, and it has been geologically active for essentially all of that time. Plates have assembled and broken apart. Oceans have opened and closed. Mountains have risen and been leveled. Ice sheets have advanced and retreated. Mass extinctions have emptied the world, and evolution has refilled it, each time with a different cast of organisms shaped by the conditions that survived the catastrophe. Through all of it, through every supercontinent and every impact and every volcanic winter, the rock cycle has continued, matter cycling through its forms with the quiet persistence of a process that has no purpose but also no end. The Earth is not heading anywhere. It is simply continuing and continuing and continuing. The human relationship with rock is older than our species. The first stone tools appear in the fossil record 3.3 million years ago, made by hominins who had not yet become Homo sapiens, who had not yet developed language or art or the symbolic thought that would eventually produce a civilization capable of understanding what rock is and where it comes from. Stone was the first technology, and it remained the primary one for nearly 3 million years of human prehistory, during which every cutting edge and grinding stone was made from the same geological raw material that had been cycling through the earth for billions of years before any hand touched it. The rock was here long before us. It will be here long after. Our entire story fits inside a single layer, thinner than a page. What geology offers, more than information, is a particular kind of perspective. The things that feel permanent, the landscape, the coastline, the mountain on the horizon are, on the timescale of the Earth, as temporary as everything else. The things that feel like disasters, the earthquake, the volcanic eruption, the flood that carves a new channel, are, on the same timescale, the normal operation of a living planet, the means by which it recycles its materials and maintains the conditions that make the surface habitable. The perspective does not diminish the difficulty of living through these events, but it changes what they mean. The Earth is not hostile, it is not indifferent in the way a void is indifferent. It is busy, endlessly, patiently busy, doing what it has always done. You are made of this. The calcium in your bones was deposited in shallow Cretaceous seas by organisms whose compressed remains now form the limestone cliffs and chalk downs of the world. The iron in your blood was forged in the cores of stars that died before the solar system existed, scattered by supernova into the cloud that collapsed to form the sun and the earth and everything on it. The water in your cells has cycled through the atmosphere, the ocean, the ice sheets, and the rock for billions of years before arriving, temporarily, in you. You are not separate from the geological record. You are the latest entry in it, a brief and extraordinary arrangement of matter that the Earth has been cycling toward for 4.5 billion years, without knowing it, without intending it, and without needing to. The ammonite on the desk made it this far. Through the extinction that ended its lineage, through the burial and the chemistry and the millions of years of rock pressing down on rock, through the uplift and the erosion that eventually brought it back to the surface where a hand could find it and carry it onto a ship and set it on a desk beside a lamp burning low in the last hour of the night. The stone remembers everything it has been through. It simply does not speak of it. And you, listening to the fire and the water and the slow settling of the ship on the dark water outside, do not need to speak of it either. The rock is patient, the night is long, and you, at last, can rest. Good night.